Today, we expect websites to deliver dynamic content personalized for us. To do this, websites display lots of elements provided from a database. Modern websites rely on a SQL backend in order to provide their dynamic content. However, if a web designer doesn't code the interaction between the website and the SQL database securely, an attacker can take advantage of those mistakes to sneak unexpected SQL queries to your database server. Let me show you an example. Here's a fake e-commerce site. Before I attack it, first let's see how it's supposed to work. If I log into the site using a valid username and password, don't use this password in real life, by the way, I can see order information that belongs to this user, including how much he spent on certain orders and his credit card information. Looks like this user spent quite a bit of money. On the flip side, if I log in using invalid credentials, I get a failure. So far, the e-commerce site works as you'd expect. However, this page is coded insecurely. Up here, I've pasted the actual SQL query this site's web code uses to log users on. To paraphrase it, this query checks every record in the user table to see if the supplied username and supplied password matches a user record stored in the database. It does this by repeatedly performing a Boolean operation on every user record in the user table. The Boolean operation is, does the supplied username match the record username, true or false, and does the supplied password match that user record? The and here is very important. When and is used in Boolean statements, both sides of an equation must be true in order for the statement to be true. So what's the problem? In this case, the web designer calls a SQL query right in his web code, leaving placeholders where a visitor or attacker's input can directly modify the query. Let me show you how. First, the attacker knows that the web coder expects a string value for a username. In SQL queries, you need to surround strings with single quotes. So by entering a single quote here, the attacker is effectively finishing the username portion of this query, giving him the opportunity to start adding new SQL code. This also has the result of returning a blank username to the query. Next, the attacker adds his own SQL code, starting with an OR statement. Remember Boolean math? The original query used an AND statement, which means both sides of the equation need to be true for the whole statement to be true. With OR, only one side needs to be true for the statement to be true. The attacker follows this OR with the statement 1 equals 1. Now, I think you'd all agree that most computers consider 1 equals 1 to be a true statement. So the OR statement, followed by a 1 equals 1 statement, creates a Boolean statement that's always true, regardless of what's in the username. In other words, the login logic will now authenticate me even though I'm not associated with any user record. But I'm not quite done yet. Because the original SQL query includes more code after the username section, the attacker still needs to do something to nullify that remaining code. He starts by adding a semicolon, which tells SQL to start a new statement. Then he adds this double dash. In SQL land, a double dash tells SQL that everything following is a comment, not code. This nullifies the rest of the original query. So my SQL injection has made it so that SQL doesn't care about a password, but the web app is coded not to accept the blank password field. So I still need to type something here, but anything will work. Look at that. We have the contents of every user record. Remember, the original SQL statement was designed to go through all the user records, returning their contents only if the Boolean statement was true. And that's just the tip of the iceberg. Once the attacker realizes he can hijack the original query using that single quote, he knows he can inject any SQL query into this field. Let me quickly show you one more example. I won't explain the SQL query in as much technical detail, but it basically updates the price records in the database. By the way, this query doesn't bother to hijack the original SQL login logic. As a result, when I submit it, the web app will say my login failed. Nonetheless, the SQL query I injected still ran. Let's check out the results. Let me just log in again as that valid user and look at the prices of this user's order. They've all been changed to 1 cent. So that's a quick demo of a very basic manual SQL injection. Keep in mind there are many ways an attacker can pull off this sort of attack, and they don't always involve the attacker manipulating input fields on a website. For example, attackers can also manipulate URLs.